Well, hi everybody. I have spent a ridiculous amount of time preparing this video. I would so much rather have been giving it to you in person today. But let's get to it. So we'll talk about graphs of other trigonometric functions. I hope you were successful in graphing sine and cosine on the test. Those are the fundamental building blocks really, and everything else stems from those. If we understand graphs of sine and cosine, we can graph everything else. And so I'm going to be describing to you how I graph some things by hand, and especially from section 6.2 and 6.3 in your textbook. It should be emphasized, though, that we should not do this alone. Like, we can use graphing calculator, and of course we could use Desmo, so I hope to show you that in person, hopefully next Monday. But let's get to it. The graph of tangent, really, there's two key features. Where is it zero? And where does it have vertical asymptotes? And so if you look at the formula sine over cosine, where is it going to be zero is when the numerator is zero. In other words, it's going to be zero when sine is zero. Well, sine is zero at multiples of pi, right? So I've graphed sine in purple here, as you can see. And wherever sine is zero, right, there is a corresponding zero of the tangent function. Now, where is it going to have a vertical asymptote? Well, that's where it's got division by zero. That's where cosine is zero. Well, cosine is zero at like half integer multiples of pi over 2. Like plus or minus pi over 2. Like here and here, cosine is zero here. I've graphed the cosine in green, right? So you divide sine and cosine, that gives you tangent by definition. And so, very simply, we can put vertical asymptotes every place there's a zero for cosine. And we put a 0, that is an x-intercept, for the tangent everywhere there's a 0 for sine. And then we graph. And so, now, notice that the period of tangent, unlike the period of sine and cosine, is 2 pi, right? Every 2 pi radians we recycle back around the unit circle. But in contrast, tangent is kind of funny. Tangent's got a period of pi. It repeats itself if we go from here to here to here. These likewise similar points are pi separated. So the period of the tangent function is pi. Now, to determine whether tangent's positive or negative, we can actually think about using, this little chart down here. Remember our kind of quadrant idea. And so since tangent is positive if both the sine and the cosine are positive or negative, oops, or they're both negative, right? Either you can get a whatchamacallit here, you can get a positive either from plus plus or from minus minus, right? So when we think about tangent, where is tangent positive? Well, tangent's positive wherever, if sine and cosine both positive or both negative. So tangent is positive in quadrants 1 and also quadrants 3. Whereas tangent is negative in quadrants 2 and quadrants 4. As we're going to be talking about the inverse tangent, this is actually really important because inverse tangent, as we'll see, actually always puts you back in quadrants 1 and 4. Inverse tangent's never going to tell you an angle over in quadrant 2 or quadrant 3. So inverse tangent, you got to be careful. And it starts with understanding this right here, so. Alright, so let's look next here about, let me just remind you of the story of modified graphs. So much of section 6.2, really, when you get right down to it, is just applying the principle of shifting or modifying graphs to the context of trig functions. So I would just remind you, if we add c, so assume c is positive, we're given a graph f of x. If we add c, we shift vertically c units. If we take the argument and replace it by x minus c, we shift right c units. If we multiply by c, we stretch vertically by a c scale factor. if we replace the argument with cx, we compress horizontally by a c factor, or alternatively, you could say we stretch by a 1 over c factor. So like if I had x over 2 here, that would stretch the graph out horizontally by 2. And then of course we got your negatives that flip over the x-axis for minus f of x, or flip over the y-axis for y equals f of minus x. And of course these all can be combined. All of the theorems in boxes in section 6.2 are these rules applied to functions. Let's take a gander here. Let's take a look-see. Let's see here. So like, here's your textbook, right? And they've got all these lovely little theorem boxes in in this book here, which is lovely and inexpensive. Like graph of y equals a tangent bx. So a is a stretching factor. The period is pi divided by b, because the ordinary period would be pi, so you put bx there. That makes it have period pi over b, and that's absolute value of b, because they want to allow for the case it's negative. And then here's some comments about domain and asymptotes and such. But really, get right down to it. All of these little boxes in this whole section, section of your book, this one is the same, right? Like features of the graph y equals a tangent bx minus c. Again, like the a is a stretching factor. The period has to do with the multiplication of x by b, it's pi over b, and basically that shift is just shifts it and so here it explains. Anyway, so this is, these are nice, and I wouldn't recommend you try to like memorize all this or anything. I wouldn't even put it on a 3x5 card, except as like a general principle. Maybe you guys might do that, I don't know, but these are just that general principle of shifting graphs applied to the tangent function. And I really think, it's good to read and to meditate on and think about what that means. But, all these little theorem boxes in this section, lovely as they are, they're part of a general principle. And I would rather you understood the general principle even than to memorize those boxes, of course. And also just that you would, as we'll hopefully explore together, see how we can use Desmos or something like that to graph it directly. Now, there is merit in doing things by hand, and let's do that. So here's an example by hand that puts in these practice. So here we have y equals 3 times the tangent of pi x over 2. So this 3 stretches it vertically, and the fact that I'm multiplying by pi over 2 in the argument means it's stretching by 2 over pi. So a simple way to create a new graph from an old is to take the features which are characteristic of the graph and to modify those features and see where they go. So the original zeros of tangent are minus pi, 0, pi, 2 pi, as we discussed. The original vertical asymptotes are at half integer multiples of pi over 2, like so. So if I'm replacing it with an argument of pi over 2 times x, I can multiply my original features by 2 over pi, because that's how they're stretching. That's how they're, all right? And so like when I multiply that through, I get minus 2, 0, 2, 4, dot, dot, dot. Multiply this, the pi's cancel, the 2's cancel, and I'm left with like odd integers, right? And that gives me this picture down here. So I've got zeros at even integers in my new graph, my modified graph of tangent, and I've got vertical asymptotes at the odd numbers, like plus or minus 1, plus or minus 3, This is minus 1, and that's 1, and this is 3, and this is 5, and so forth. And so that's a really decent way to make a new graph from an old one. If you understand the critical thing, which is I know my graph of sine, I know my graph of cosine, I know my graph of tangent. We can go quite a ways from those. Let's look at another example. So so we can talk about the reciprocal trig functions, right? Like, here is the graph of secant. So secant's 1 over cosine. Now, when is that 0? Well, it's never 0, right? Because you can't make 1 over cosine equal to 0. more to the point, the cosine is bounded by 1. The absolute value of cosine x is less than 1. So if you flip that inequality, that gives you 1 over the absolute value of cosine is greater than or equal to 1. What that means is that the graph of secant is stuck outside the band y equals plus or minus 1. It's stuck outside that band. The smallest that secant can be is the largest that cosine can be, essentially in magnitude. So like where cosine is 1, for example, cosine of 0 is 1, is where secant's the smallest. Where cosine is minus 1 at like pi or minus pi, that's where secant bumps up against that y equals minus 1. I don't want to say it's the largest, of course, because secant's larger up here. But that's basically the graph. It's these sort of upside down, they're going asymptotically to places where cosine is 0. And again, so where cosine is 0 is really a lot of it. And then the fact that it has to be stuck outside y equals, absolute value of y equals 1 is the other part. You know those two things, you could easily graph secant just like that. Notice that the range of secant is minus infinity to minus 1, union with 1 to infinity. That's actually also, although I didn't write it on this page yet, come on, where's my purple marker? That's also actually the case, that's the range for cosecant x for essentially the same reasons in my next example. So again, let's look at it. All right, let's look at it. Let me get these pages out of the way here. I'll come back to those. So, secant x, cosecant rather, is 1 over sine. Excuse me, still recovering. So, since sine is bounded by 1, 1 over sine can't be smaller than 1. Which means that y equals cosecant is stuck outside of the absolute value of y equal, less than 1 band. So that helps me draw. So I just draw these like green lines to tell me, hey, cosecant's stuck outside these. And again, the smallest that cosecant can be is like basically where the sine is largest because it's 1 over it, So of course at pi over 2, we know that sine of pi over 2 is what? Sine of pi over 2 is 1, right? So that gives me this point right here, right? That point right there, for what it's worth, is pi over 2, comma 1. And so it opens up from there, and of course it's got vertical asymptotes where sine is 0, namely plus or minus, multiples of pi, right? So that's it in a nutshell. Like pretty much you can graph any of these reciprocal functions, these tangent functions, by hand if you got a little bit of time and a little bit of patience. You just need to be aware of, I'm looking for where my zeros are, if there are any. There aren't any here. Or I'm looking for where my vertical asymptotes are. And I'm also like, it's of course important to keep in mind just, the nature of sine and cosine, namely that they're stuck between plus or minus 1. If you understand those principles, and the shifting of graphs, of course, you can graph pretty much everything. Now, I've assigned you about 5 to 10 problems from section 6.2. Please work through them. Try to draw them out for yourselves. If you need to use a graphing calculator to help you, that's fine. But let's try to understand, how to decide which one of those shapes is. What you should be looking at in terms of your understanding from homework is, like, can I recognize what a tangent looks like? What does a cotangent look like? What's a secant look like? What's a cosecant look like? And these are not disjoint cases, right? Like if you really look at this, the graph of secant and the graph of cosecant, it's the same graph, right? If you ignore exactly where stuff is, like it's the same scale. They're both opening up beyond plus or minus 1, right? So anyway, I hope that we can spend some time doing more of this with Desmos together. I don't have a good way to do that with videos, honestly, at the moment, so my apologies. Let's move on to section 6.3. As you know, I have burnt a few of our class days with my foolish getting sick, how dare I. And so we got some ground to cover here. And but I'm not just going to dive into section 6.3 without a discussion, because I think it's important for us to remember what an inverse function is. All right, so let's talk about it. An inverse function, if you have a function from a to b, a one-to-one function, which means that, you know, if you have f of a equal to f, if you have f of x1 equal to f of x2, it forces x1 to be equal to x2. Now, that one-to-one function criteria we can also understand by the horizontal line test you may recall. Anyway, then the f inverse, the inverse function from b to a, well, it's called the inverse function, and we define f inverse of y to be equal to x if and only if f of x is equal to y, which is to say that the inverse function undoes the function. Alternatively, the inverse function and the function are related by these two relations. Right? These actually show you how you can use the inverse function to solve equations involving the function. First of all, f of f inverse of y is equal to y for all y and b, and f inverse of f of x is equal to x for all x and a. Notice that this is with y and this is with x. This is from b and this is from a. They don't have to be the same set, and these conditions are generally, there's strings attached. Has to be, the context matters. You can't just, do these willy-nilly without paying attention to the domain and the range of the function. Notice also that the domain of the function is the range of the inverse function, and the domain of the inverse function is the range of the function. These are very helpful guides as you're understanding the interplay between a function and its inverse. Now here's an example of how to calculate the formula for the inverse function. All right, just to give you a walk down memory lane here. So if I have f of x is, and this will also illustrate my range and domain comment here in a second. F of x equals 3x minus 2 over x minus 1. There's a given formula. So I look at that, I go, okay, so the domain is reals, take away 1, right? We can't have division by 0. So I got to throw out 1. Now to calculate the inverse function, I simply solve the formula for x. So I do that here. Multiply by the denominator. X minus 1 times y is 3x minus 2. Xy minus y is 3x minus 2. Put all my x's in one basket. Put all my y's on the other side. Factor out y minus 3. Divide by the factor. I get x equal to, excuse me, y minus 2 over y minus 3. So f inverse of y is y minus 2 over y minus 3. Now you can see that the domain of the inverse function has to exclude 3. And so if you believe what I wrote up in the green, you also know that this is equal to the range of the function. And you also know that this is equal to the range of the inverse function. Right? And that's exactly what happened. Excuse me, range. Wait a minute. My bad. Inverse function, range. Yeah, I guess so, because the inverse function can't. Goodness. It doesn't ever actually reach 1. It's not, I guess it's not immediately obvious, but if you did the, here's a formula for this. I'm going to mess this up. So that's, let me just, that would be y minus 3 plus 1 over y minus 3, right? Which is 1 plus 1 over y minus 3. So you can see from that formula right there that the value of the inverse function, right? You can see from that formula that the value of the inverse function never reaches 1. It's always above or below 1, which is 1 is not in the range of the inverse function, which, as I forecasted up here, is totally unsurprising, right? So anyway, there's this interplay between the range of the function and the domain of the inverse function. It's important to understand. And here's a sad graph of the function. I was going to try to graph the inverse function there too, but it just got way too messy. So I think I have a better example next. Let me see what page I'm on. 3. Here's 4. Cannot emphasize to you how much easier this lecture would have been to give you in person. This graphing ahead of time, really a drag. All right, so here's an example. Y equals f of x and y equals f inverse of x. How do they relate graphically? So if we have y1 is f of x1, then f inverse of y1 is equal to f inverse of f of x1, which is equal to x1, right? In other words, if x1, y1 is in the graph of f, then y1, x1 is in the graph of f inverse. So here's a hypothetical, I didn't even give the formula, just here's a picture. So a given green graph, y equals f of x, and I tracked a couple points, like, so the point -5, comma 0.5 is on the given graph of the function. So that means that the corresponding flippity-floppity down here, 0.5 -5 is on the graph of the inverse function. That point tracks to that point. And likewise up here, this point, 5,25, tracks up here to this point, 2.5, comma 5. See, we flippity-flop, going from the function to the inverse function. Now, this is not entirely easy to see, but if you think about like just graphing this, right? We graph like this, right? And so, on the other hand, we graph the purple like this, So it's the same graphing process actually. It's just x and y's roles are being interchanged, right? We're graphing from right to left. We're graphing from down to up. But it's the same shape if I did my job right. And so this is the remark. To graph, this is really the key idea here. To graph y equals f inverse x, we simply graph y equals f of x, but we swap the roles of x and y. Like, oh, well this should be easy then. His sine, right? Here's like a, is that sine? Actually, that looks like minus sine, doesn't it? I graphed minus sine here, didn't I? So here's a graph of minus sine, and then, oh, I can't. Sad. Well, I tried anyway. My point is I could graph this and then take the same wiggly and just go this way instead. That would be the inverse function. But then what's the problem? We have failed the vertical line test. Oh no. Right? There's many outputs for one input, so that's not the graph of a function. So what do we do? How do we reconcile this? And that's really where the interesting aspect of inverse trig functions comes into play, because the truth of the matter is it's really one of your first genuine exposures to the concept of a restriction of a function. So what's a restriction of a function? Well, actually, like I said, truth be told, the inverse functions are actually local inverses. When we talk about inverse sine, inverse cosine, inverse tangent, we're not talking about global inverses for sine and cosine and tangent. There is no global inverse because sine and cosine and tangent repeat. So if you just try to flip their graphs, you fail the vertical line test. So we need to select subgraphs of sine, cosine, and tangent for which the graphs pass the horizontal line test. And so our custom, and it is just a custom because if you think about it, you could pick other parts of the graphs. You can pick other parts of the graphs of sine, cosine, or tangent which don't repeat. But this is what we do. We look at sine from minus pi over 2 to pi over 2. That gives us a stretch of the sine graph which passes the horizontal line test. I can one output, right? Only one output is, each output's reached just once. If I have sine of x1 equal to sine of x2, subject to this condition, then x1 must be equal to x2. If I have tangent of x1 equal to tangent of x2, where x is coming from this little range here, it forces x1 to equal to x2. If I have cosine of x1 equal to cosine of x2, and x1 and x2 are stuck between 0 and pi, then x1 is equal to x2, you see? Sine and cosine and tangent, they don't repeat themselves if we restrict down to these domains. And so with respect to the restricted domains, we define the inverse sine, the inverse tangent, the inverse cosine, and you can get their graphs simply by interchanging the roles of x and y. So for example, this point pi over 2, 1 becomes the graph, becomes the point 1 over 1 comma pi over 2 and the inverse sine. This point minus pi over 2 minus 1, it becomes this point minus 1 comma minus pi over 2 on the graph of the inverse sine. Also notice that at the edges of the restriction domain, you have horizontal asymptote. You basically have a horizontal tangent here, right? You could put a marker. It'd be flat like that, right? It'd be flat like that. These are horizontal tangents, and when you go to the graph of the inverse function, the horizontal tangents become vertical tangents. That's something to look for as you're thinking about inverse functions. Horizontal tangents become vertical tangents, and vice versa. The vertical tangents in the graph of the tangent restricted become horizontal tangents in the graph of the inverse tangent. Right? See that? That's what happens. You had vertical asymptotes at pi over 2 and minus pi over 2. For the graph of the inverse tangent, you have horizontal asymptotes at plus or minus pi over 2. And cosine, well, cosine is going from 0, 1 to pi minus 1. So inverse cosine is flippity-floppity. 0, 1 becomes 1, 0. Pi minus 1 becomes minus 1 pi. And this x-intercept becomes a y-intercept. We go from pi over 2, 0 instead to 0 pi over 2. And so all of the shapes, but mind you, the shapes of inverse sine, the shape of inverse tangent, the shape of inverse cosine, it's the same exact shape as was for sine, for tangent, for cosine. It's just that they're running in the y rather than in the x. Understand that. Now, also understand that these are definitions. So when you use your calculator, let me write it out here. Still got a little bit of time to write, right? Yowzers, Bowsers. This is wearing me out. Stupid COVID pneumonia. I tell you what, don't ever get it. Alright. But anyway, if you do get it, get yourself some ivermectin. Made me feel better. And also, stay out of the hospital. They'll kill you there. 7. I was about to go to the hospital. Instead, I decided to take the doctor's advice, sleep on my belly, walk around, stretch my lungs out. You know what? I got better. I got better pretty fast, actually, once I started sleeping on my belly and taking the advice to move around every hour. That's so important. So many people are just sitting in a chair, filling their lungs full of garbage. You got to get up. You got to walk around. And I also had the antibody treatment. That was really helpful. All right, I'm digressing. Anyway, let's see here. So, definition. So here we have sine of inverse sine of x, that will be equal to x, and sine inverse of sine, I'll use y this time, is equal to y. Now what are the conditions here? So this is true for minus pi over 2 less than or equal to y less than or equal to pi over 2, because that's where inverse sine is the inverse for sine. And the top one, on the other hand, is a little bit easier. Minus 1 less than or equal to x less than or equal to 1. That's how inverse sine is defined. Alright, let me give you an example of this. Let's use my handy dandy calculator here. Now, of course, this is all for radians. Although you can do it in degrees, right? I mean, I'm writing these things for radians, but you can convert all of these statements over for statements about degree functions if you want. But let's try it out. So what should happen if we try sine inverse of 0.5? What's that going to give us? Let's get out my handy dandy calculator here. And what mode am I? I'm in degree mode. That's not good. Let's fix my mode. I'm here in my mode. Stuck in my mode. Oh no, I just can't change my mode. Somebody should make a song about that. Come on, mode. Mode! You jerk. Come on. Shift setup. Shift setup. There we go. 4 for radian. Alright, inverse sine 0.5. What are we going to get? We're going to get pi over 6. What do you know? Pi over 6. Why is that? Since we don't, this isn't surprising to us, because we know that the sine of pi over 6 is equal to 0.5. Right? So very good. Now let's try another experiment. What happens if we do inverse sine of 2? Inverse sine of 2, let's try it out. What's going to happen? Works for a half, it should work for 2, right? Oh no, error! But that's not surprising, because inverse sine is only defined for inputs between -1 and 1. If you try to take inverse sine of a number larger than 1 in magnitude, you're basically asking the question, what angle is sine equal to that number larger than 1? And that's like impossible, because sine is stuck between -1 and 1. So there you go. Alright, so there's an example. Now, how about the definition of cosine? How's cosine go? Cosine of cosine inverse of x. Well, this is easy. It's equal to x, or -1 less than or equal to x less than or equal to 1, right? On the other hand, inverse cosine of cosine of y, well, that's going to equal to y for 0 less than or equal to y less than or equal to pi. That's the definition of inverse cosine. So inverse cosine is always going to give you back answers from 0 to pi, right? So like, let's look at an example. Alright, I'll try to show you some of the danger here. So let's try to inverse cosine. Oh, let's try 0.5 again. Why not? That's a fun one. Alright, inverse cosine 0.5. I get pi over 3. Pi over 3. That's not surprising, because we know what? The cosine of pi over 3, which is 60 degrees, is 0.5, right? Now you won't, I'll do it again. Inverse cosine of 3, what's going to happen? Oh no! Well, inverse cosine of 3, better tell us, go fly a kite, right? Oh, error, error. Of course, because you can't have cosine of an angle equal to 3, right? Now, a little bit of a cautionary tale here. How about, let's kind of set us up for the fail a little bit here. Cosine, well, cosine of, let's see here, how about cosine of minus pi? Cosine of minus pi, what is that? Cosine minus pi, it's equal to -1. So then, what happens when we take inverse cosine of cosine of minus pi, right? So that should be inverse cosine of -1, right? But what happens? What's going to happen here? Something funny is going to go on, right? Now, if you're just kind of just not minding your business and just going, oh, okay, well, inverse cosine of pi, that should just be minus pi. This should just be minus pi again, right? Right? All right. And but what is inverse cosine of -1? Inverse cosine of -1. Well, I get pi over here. Wait a minute. How can that be? So why didn't this work out? Well, the answer is that this simplification, bogus. I'm not following the rules. You know, this, keep in mind that the cosine inverse of cosine of y is equal to y again only for 0 less than or equal to y less than or equal to pi. And of course, minus pi is not in here, right? So we shouldn't expect that to happen. So we got to watch out. We got to remember what inverse cosine does. It always gives us back an angle between 0 to pi, all right? And then, see, I'll use another page. I'll try to scan all these for you guys. Oh, goodness gracious. Sorry, this lecture might go a little short. Run out of energy. Definition. So, tangent of inverse tangent of x is equal to x. Now this time, good news. No strings attached here for x in the reals. And inverse tangent of the tangent of y. Well, my choice of x and y here is not terribly, I'm probably not being consistent, my bad. Well, anyway, this is equal to, I just want to use a different letter because it does matter. This is for pi over 2, minus pi over 2, less than y, less than pi over 2, right? So, again, inverse tangent is only going to give you back angles between plus or minus pi over 2, all right? So, like, just to give you an example how this works, if we have, let's calculate the inverse tangent of, let's say, 2. See what our handy dandy calculator tells us here. Inverse tangent of 2. Whoa. 1.1071 for dot 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 dot. Alright, I mean, I guess 9 dot 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 dot, whatever, it's approximate, right? And that makes sense because if we calculate the tangent of 1.107149 dot 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 dot, what do we get? Let's try it out. Tangent of answer, and lo and behold, 2. Right? So that's how the function and the inverse function work, right? They undo each other. Now, now let's see here. Let's try to get ourselves into some trouble. Try to get ourselves into some trouble here to end the lecture. Well, how about this? The tangent of the tangent of pi. Well, we know what that is. Tangent of pi is equal to 0, right? So let's take inverse tangent. Take inverse tangent of this formula. And let's see what happens if we're careless. So inverse tangent of pi, it should be equal to inverse tangent of 0. So, okay, again, playing the fool, ignoring what I just wrote up there, right? This would simplify to pi, right? But what's our calculator give us inverse tangent of 0 equal to? Inverse tangent of 0 is 0. We can't have, but wait a minute, how can, what? It's because I'm ignoring the terms and conditions. Inverse tangent up here always goes between minus pi over 2 and pi over 2. I can't simplify inverse tangent and tangent unless I also know that that y is where it's supposed to be, which is between minus pi over 2 and pi over 2. Only there does inverse tangent actually serve as the inverse function to tangent. Other places, you know, no game, no success. And this is not an insurmountable problem. It's just this is a wrong calculation, and we need to be aware of it. All right. So in future lectures here, we're going to talk about how to use the inverse trig functions to solve problems, and it's really simple. We just have to keep in mind what they're giving us. They're going to always be giving us an angle between minus pi over 2 and pi over 2 for like sine and for the inverse sine and the inverse tangent. And they're always going to be giving us an angle between 0 and pi for cosine. And then once you know that, you can kind of extrapolate from there. Actually, let me just give you one example of that. And we kind of did this before in class, I think, but you know, if I wanted to solve like, you know, say sine, try to solve sine of x equal to, like, you know, minus a half, let's say. Right, so like graphically I can anticipate what that's going to look like, because here's minus a half, right? So I know there's all these solutions. So I'm looking for these points, right? So to get started on one of those, I mean, this is an easy thing. You wouldn't need a calculator for this anyway, but you know, the calculator can help now if you understand. So if I take inverse sine, of sine of x is inverse sine of minus 1/2, how does that work out, you know? Well, that's going to give me x is equal to inverse sine of minus 1/2. But what is it? Where is that going to be? Which one of these is that going to be? Well, remember, inverse sine is the inverse for sine restricted from minus pi over 2 to pi over 2, right? It's from this stretch that it's serving as the inverse function. So I can already tell you what's going to happen when I use my calculator. It's going to tell me that point right there, right? It's going to tell me minus pi over 6, I think, actually. Inverse sine of minus 0.5. Minus pi over 6, as I said, right? So now once you know that, that gives you a leg to stand on. So you've got that one point, right? And then you can kind of extrapolate and find those other two infinite families like we kind of talked about in the other example before. But we'll get more back into that in a future lecture. Just wanted to warn you, inverse sine, inverse tangent, inverse cosine, they do come with strings attached. We must be aware of those strings. All right. So let's just take a quick look at section 6.3 together. I got this thing going. Maybe there's some other cool bits in there that I've missed in my quick rundown here. Let's see here, section 6.3, right? All right. All right, come on. So here it is. Let's see here, inverse sine, inverse cosine, inverse tangent, very good. They have some even nicer pictures than I do, right? There's their picture of tangent, and where's their picture of inverse? Well, oh, that's just the picture of the restricted tangent, great. Here's a picture, here's their picture of, they do have some nice pictures of both, oh, come on, zoomy zoom. They do have a nice picture here of both the sine and the inverse sine on the same picture. That's really nice. Likewise over here, here's a picture of the cosine and also the inverse cosine in the same picture. Super nice. I think my picture of tangent's better. Here's their picture of tangent. Here's their picture of inverse tangent. Mine's better because it's got the asymptotes, and the asymptotes are really, man, they're really part and parcel for what's going on there. They don't have asymptotes in those pictures. I think that's a mistake. But anyway, and here, you know, here are those rules I was just telling you about, and then they got some examples involving exact expressions, which we could talk about when we meet again, perhaps, if you want, and somehow about how to use a calculator. And yeah, maybe we'll start with some of these examples when we meet again here. Maybe. This text box, I think, is everything I told you actually today. So, and here's just some nice. So these are good examples. Please do read the section. I never have time to cover everything in this book during your lecture. Actually, I do my best, and so I'll assign probably more of these, and hopefully repost the course planner so you know what to do. So, thanks, guys. I think that'll be it for today. Apologies, my breath is getting better, but hopefully by Monday I'll be. Well, we'll see. My wife may keep me home Monday. We'll see. I can't make any promises just yet. So sorry, guys.